Welcome to DAR Tutors for online and home tuition. In this video, we will explore Chapter 8 of the IB Mathematics Applications and Interpretation Higher Level textbook, the unit circle and radian measure. This is a foundational topic for understanding trigonometry and its applications. Our focus will be on the core concepts required for the IB AIHL syllabus. We'll begin with radian measure, which provides an alternative and often more convenient way to measure angles. From there, we'll develop the unit circle and use it to define the trigonometric ratios for any angle. Next, we'll dive into the important exact values for common angles like 30, 45, and 60 degrees. We'll then establish a crucial relationship between the three main trigonometric ratios, the Pythagorean identity. Finally, we'll see a powerful application of trigonometry, how the tangent of an angle relates to the gradient of a straight line. We'll work through numerous examples and conclude with IB-style practice questions to solidify your understanding. By the end of this session, you will be able to convert between degrees and radians, apply the formulas for arc length and sector area, use the unit circle to define and find trigonometric ratios, apply the Pythagorean identity, and connect trigonometric functions to linear algebra by calculating the gradient of a line from its angle with the x-axis. We begin with the first objective: to understand and apply radian measure. Radian measure is an alternative to degrees. A radian is defined as the angle subtended at the center of a circle when the arc length is equal to the radius. So, if the radius is r and the arc length is also r, the angle is exactly 1 radian. This is a very natural way to measure angles, as it relates the angle directly to the geometry of the circle. A full circle is 360 degrees. What is it in radians? The circumference of a circle is 2p times the radius. So, in a full circle, the arc length is 2p times the radius. This means a full circle has an angle of 2p irradians. Therefore, 360 degrees is equivalent to 2p irradians. This gives us our fundamental conversion factor. It's often more convenient to simplify this by dividing by 2. So, 180 degrees is equal to p irradians. This is a key identity that you should commit to memory. It allows us to convert between the two systems. To convert from degrees to radians, we multiply by p over 180. To convert from radians to degrees, we multiply by 180 over p. Let's work through some examples. First, let's convert 45 degrees to radians, expressed in terms of p. We multiply by our conversion factor, p over 180. 45 divides into 180 4 times. So, 45 degrees is p over 4 radians. The degree symbol is always used for degrees, but for radians, the little c or rad is often omitted. Now let's convert a more complex degree measure like 126.5 degrees to radians. For this, we'll give our answer as a decimal. We multiply by the same conversion factor. Using a calculator, this gives us approximately 2.21 radians, rounded to 3 significant figures. Remember, radians can be expressed both in terms of p for exact values, or as decimals for approximations. Now, let's go the other way and convert from radians to degrees. Let's convert 5 over 6 radians to degrees. This time, we multiply by 180 over p. Notice how the p terms cancel out, which is very convenient. We are left with 5 times 180 divided by 6. This simplifies to 5 times 30, which equals 150 degrees. Let's try another one with a decimal. Convert 0.638 radians to degrees. We multiply by 180 over p. Again, using a calculator, this gives us approximately 36.56 degrees. We'll round this to 36.6 degrees to 3 significant figures. As a final exercise for this section, let's fill in a conversion table for some common angles. Let's complete this table, converting each degree measure to its radian equivalent in terms of p. You can pause the video and try this yourself first. Here are the solutions. Notice the pattern. 45 degrees is p over 4, and the subsequent angles are simply multiples of p over 4. For instance, 135 degrees is 3 times 45 degrees, so it's 3 over 4. To recap, we have now met our first objective. We can define a radian, and we are able to convert between degrees and radians using the key identity that 180 degrees equals perradians. These are essential skills for the topics that follow. Our next objective is to find the length of an arc and the area of a sector of a circle when the angle is given in radians. We can build on our definition of a radian for this. Remember, an angle of 1 radian corresponds to an arc length equal to the radius. What if the angle was, say, 2 radians? The arc length would be twice the radius. If we generalize this, for any angle θ in radians, the arc length L is simply the radius r multiplied by the angle θ. So, LEC as an art. It is absolutely critical that the angle θ is in radians for this formula to work. If you are given the angle in degrees, you must convert it to radians first. For the area of a sector, we use a similar principle. The area of a sector is a fraction of the area of the whole circle. The area of a full circle is p times the radius squared. So, the area A of a sector is the fraction θ divided by 2p, all times per squared. The p terms cancel out, simplifying the formula to A equals 1/2 r squared t. Just like with arc length, the angle θ must be in radians. Again, if it's in degrees, convert it first. These formulas are significantly simpler than the degree versions, which require dividing by 360, which is why radians are so powerful in calculus and advanced mathematics. Let's work through an example. A sector has a radius of 12 centimeters and an angle of 3 radians. We need to find its arc length and its area. First, the arc length. We use the formula L equals RD. The radius is 12 and the angle is 3. So 12 times 3 gives us 36 centimeters. This is straightforward because the angle is already in radians. Next, let's find the area. We use the formula A equals 1/2 r squared θ. Plugging in the values, we get 1/2 times 12 squared times 3. That's 1/2 of 144 times 3, which is 72 times 3, giving us 216 square centimeters. Let's try a different type of problem. This time, we're given the radius and the arc length, and we need to find the angle and the area. A sector has a radius of 8.2 centimeters and an arc length of 12.3 centimeters. First, let's find its angle, which must be in radians. We rearrange the formula L equals rad to make θ the subject. Θ equals L over r. Substituting our values, we get 12.3 divided by 8.2, which equals exactly 1.5 radians. Notice there are no units for radians in the answer, as it is a pure number representing a ratio of lengths. Now we can find the area using our new value for θ. A equals 1/2 r squared θ. This is 1/2 times 8.2 squared times 1.5. This calculation gives us an area of 50.43 square centimeters. For our final example in this section, let's look at a problem that mixes radians and involves a conversion. A sector has radius 9 centimeters and an angle of 7m over 4 radians. We need to find both its arc length and its area. The angle is already in radians, so we can proceed directly. For arc length, L equals RD, which is 9 times 7p over 4. This simplifies to 63p over 4 centimeters. We can leave this as an exact answer in terms of p. For the area, A equals 1/2 r squared θ, which is 1/2 times 9 squared, times 7p over 4. This becomes 1/2 of 81 times 7p over 4, which gives us 567p over 8 square centimeters. In summary, we have now achieved our objective of finding arc length and sector area. By using angles in radians, we use the simple and elegant formulas L equals RD and A equals 1/2 r squared θ. Always double-check that your angle is in radians before applying these formulas. Our third objective is to use the unit circle to define and find trigonometric ratios for any angle, not just acute angles in right triangles. The unit circle is a circle centered at the origin, 0, 0, with a radius of exactly 1 unit. By the Pythagorean theorem, the equation of this circle is x squared plus y squared equals 1. Now, let's consider any point P, y, on the unit circle. We'll define an angle θ by starting at the positive x-axis and rotating a line segment OP anticlockwise to reach the point P. Anticlockwise angles are positive, and clockwise angles are negative. This gives us a generalized definition of sine and cosine. For any point P on the unit circle corresponding to an angle θ, the cosine of θ is the x-coordinate of P, and the sine of t is the y-coordinate of P. This means that the values of sine and cosine are always the coordinates of a point on a circle with radius 1. Since x and y can only go between -1 and +1 on the unit circle, this implies that the values of sine and cosine can never be greater than 1 or less than -1. So, for any angle θ, the range of sine and cosine is from -1 to +1. This is a fundamental property of these functions. Furthermore, if we use the definition of cosine as the x-coordinate and sine as the y-coordinate, the equation of the unit circle, x squared plus y squared equals 1 becomes the most important identity in trigonometry. Cosine squared θ plus sine squared θ equals 1. This is known as the Pythagorean identity. Now let's define the tangent function. Imagine extending the line segment OP until it meets the vertical tangent line at the point A10. Let's call the intersection point Q. Using similar triangles, we can show that the y-coordinate of Q is sin θ over cos t. Therefore, the tangent of θ is defined as the sine of t divided by the cosine of t. A very useful alternative interpretation of the tangent is the gradient, or slope, of the line segment OP. The gradient is the change in y divided by the change in x, which is y over x. Since y is sin θ and x is cos θ, the gradient of the line OP is indeed tan θ. To recap, we have defined the three main trigonometric functions based on the coordinates of points on the unit circle. Cosine is the x-coordinate, sine is the y-coordinate, and tangent is y over x. This unit circle definition allows us to extend these functions to any angle. A key application of the unit circle is to determine the sign of sine, cosine, and tangent in each of the four quadrants of a Cartesian plane. This will be our next learning objective. We can think of the x-axis and y-axis dividing the unit circle into four quadrants. Let's analyze the signs in each quadrant. In the first quadrant, x-coordinates are positive and y-coordinates are positive. Since cosine is x and sine is y, both cosine and sine are positive. Because tangent is sine over cosine, it is also positive. So, all three ratios are positive in the first quadrant. In the second quadrant, x-coordinates are negative and y-coordinates are positive. This means that cosine is negative, while sine is positive. Tangent, being sine over cosine, will be a positive number divided by a negative number, which results in a negative value. So, only sine is positive in the second quadrant. In the third quadrant, both x and y coordinates are negative. This means both cosine and sine are negative. However, tangent is sine over cosine, which is a negative number divided by a negative number. This gives a positive result. Therefore, only tangent is positive in the third quadrant. Finally, in the fourth quadrant, x-coordinates are positive and y-coordinates are negative. So, cosine is positive and sine is negative. Tangent is a negative number divided by a positive number, making it negative. This means only cosine is positive in the fourth quadrant. This pattern of which ratio is positive in each quadrant is crucial and can be remembered with a simple mnemonic device. Starting in quadrant 1, the letters spell out ASTC. You can remember this with phrases like, all students take chemistry, or all silly turtles crawl. This tells you which ratios are positive in each quadrant. All in quadrant 1, sine in 2, tangent in 3, and cosine in 4. Any ratio not mentioned for a quadrant must be negative. We have now learned how to use the unit circle to determine the signs of the trigonometric functions in any quadrant using the ASTC rule. This will be invaluable for solving trigonometric equations and working with identities. We now come to a very important set of angles. These are the multiples of 30 and 45 degrees, or in radians, p over 6 and p over 4. Our objective is to find and memorize their exact trigonometric values. These angles, like 0, 30, 45, 60, and 90 degrees, appear frequently in geometry and trigonometry, so it's essential to know their sine, cosine, and tangent values exactly, without relying on a calculator. We can derive these values using two special triangles. First, consider an isosceles right-angled triangle with two sides of length 1. By the Pythagorean theorem, the hypotenuse is the square root of 2. The angles are 45, 55, and 90 degrees. From this triangle, we can see that sine of 45 degrees or sine of p over 4 is opposite over hypotenuse, which is 1 over root 2. Cosine of 45 degrees is adjacent over hypotenuse, also 1 over root 2. And tangent of 45 degrees is opposite over adjacent, which is 1 over 1, or 1. Next, let's use an equilateral triangle with side lengths of 2. All angles are 60 degrees. If we bisect it with an altitude, we create two 30 to 60 to 90 triangles. Each of these new triangles has sides of length 1, root 3, and 2. The angles are 30, 60, and 90 degrees. Using SOHCAHTOA on this triangle gives us the exact values for 30 degrees, P6, and 60 degrees, P3. And for 60 degrees, sine of 60 degrees, or sine of P over 3, is opposite over hypotenuse, root 3 over 2. Cosine is adjacent over hypotenuse, 1 over 2. Tangent is opposite over adjacent, root 3 over 1, or just root 3. The values for 0 and 90 degrees can be found directly from the unit circle. At 0 degrees, 0 radians, the point on the unit circle is 1, 0. So cos 0, 1, sin 0, 0. At 90 degrees per 2 radians, the point is 0, 1. So cos 2, 0, sin 2, 1. We can organize all these exact values in a table. A very helpful pattern is a quick way to remember the sine values. The square root of n, all over 2, where n is the number in the sequence 0, 1, 2, 3, 4. So for sine of u degrees, and 0, giving 0. For sine of 30, and per 1, giving 1/2. So for sine of 45 and 2, giving root 2 over 2. For sine of 60, n or 3, giving root 3 over 2. And for sine of 90, n for 4, giving 2 over 2, which is 1. The cosine values are the exact reverse of the sine values, and the tangent is simply sine divided by cosine. This makes it easy to reconstruct the table whenever you need to. Let's put this into practice. Let's find the exact values for 4p over 3. First, we need to locate 4p over 3 on the unit circle. An angle of 4p over 3 lies in the third quadrant. Its reference angle, the angle it makes with the x-axis, is 4p over 3 minus p, which is p over 3. This means it has the same trigonometric magnitude as the 60-degree angle we just derived. From our table, we know sin 3 is root 3 over 2 and cos 3 is 1/2. Now we apply the ASTC rule for quadrant 3. In the third quadrant, tangent is positive, so sine and cosine must be negative. Therefore, sin 4p3 is negative root 3 over 2, and cos of 4p3 is negative 1 over 2. The tangent is sine divided by cosine, which is negative root 3 over 2 divided by negative 1 over 2, giving us positive root 3. Today, we have successfully derived and memorized the exact trigonometric values for key angles. And we've learned how to use reference angles and the ASTC rule to find these values for any angle in any quadrant. A powerful tool in trigonometry is the concept of identities. An identity is an equation that is true for all possible values of the variables. Our objective in this scene is to explore a set of supplementary and negative angle identities. Supplementary angles are angles that add up to 180 degrees, or p radians. Let's see how the trigonometric ratios of an angle relate to the ratios of its supplement. Consider the angles θ and p minus θ. On the unit circle, p minus θ is the reflection of θ across the y-axis. If the coordinates of c are t sin θ, then the coordinates of p minus θ are as t sin th. This directly gives us the identities. The x-coordinate cosine is negative, so cos pf equals negative cos I. The y-coordinate sine is the same, so sin pf equals sin th. And the tangent is sin over cos, which gives negative tan th. These identities allow us to relate angles in the second quadrant to angles in the first. Next, let's examine negative angles. A negative angle, like negative θ, is a clockwise rotation from the positive x-axis. On the unit circle, an angle of negative θ is a reflection of t across the x-axis. If the coordinates of t are cos t sin th, the coordinates of negative θ are chi cos t a sin th. This reflection tells us that cos ta t is equal to copat das t ata, while sin kata t is equal to negative sin. And consequently, tan otka phi ate equals negative tan th. Cosine is called an even function because f(x) and sine and tangent are odd functions because f(x). Let's work through some examples that apply these identities. Suppose we know that sine of 21 degrees is approximately 0.358. Can we find sine of 159 degrees without a calculator? 159 degrees can be written as 180 minus 21 degrees. Using our supplementary angle identity, we know that sin 180 degrees 21 degree is equal to sin 21 degrees. Therefore, sin 159 degrees is also approximately 0.358. Here's another example. If tan 47 degree is approximately 1.272, what is tan 133 degree? First, we can use the negative angle identity to say that tan 133 degree equals negative tan 133 degree. Now we need to find tan 133 degree. This is tan 180 47 degree, which using the supplementary angle identity is negative tan of 47 degree. So we have negative of negative tan 47 degree, which simplifies to positive tan 47 degrees. Therefore, tan 133 degree is approximately 1.072. We have now explored and applied supplementary angle and negative angle identities. These provide powerful relationships that connect the trigonometric ratios of different angles, making it easier to solve problems. We will now develop a systematic approach to finding angles. Our objective is to find all angles between 0 and 2πr that satisfy a given trigonometric equation, such as sin phi ek or ce equals ek. For any given trigonometric ratio, there will be two angles in a full revolution that produce that value. We can find them using our calculator, the ASTC rule, and a reference angle. The general strategy is, first, use the inverse trigonometric functions like sin inverse, cos inverse, tan inverse on your calculator to find an initial angle. Second, use this initial angle to find a reference angle, the acute angle with the x-axis. Third, use the sign of the ratio and the ASTC rule to determine the correct quadrants. Finally, use the reference angle to find the two solutions in those quadrants. Let's find the two angles that between 0 and 2π such that cos phi equals negative 1/2. First, we know cosine is negative. The ASTC rule tells us cosine is negative in quadrants 2 and 3. Next, we find the reference angle. We solve the positive version of the equation, we know from our exact values that this reference angle at the base is p 3 radians. Now we use this reference angle to find the two solutions. For quadrant 2, the formula is p minus the reference angle, so Th1 equals p, p3 equals 2, p3. For quadrant 3, the formula is p plus the reference angle, so Th2 equals p plus p3 is 4 top 3. So the two angles are 2p3 and 4p3. We can check these on the unit circle. Let's verify this using a unit circle diagram. We draw a vertical line at x equals 1 trio. This line intersects the circle at 2 points, one in the second quadrant and one in the third, as predicted. The angles are 2p3 and 4p3. Here are the general formulas for finding the second angle based on the first angle, the reference angle. For sine, it's 180 or p minus the angle. For cosine, it's 360 or 2p minus the angle. For tangent, it's 180 or p plus the angle. Let's try one more with a calculator. Find all angles phi 0 equal phi 2p such that tan phi equal 3. First, the calculator gives us the initial angle. Tan inverse of 3 is approximately 1.25 radians. Since the tangent is positive, we know our solutions will be in quadrants 1 and 3. The angle we found, 1.25 radians, is in the first quadrant. This will be our reference angle. For the third quadrant solution, we use the formula for positive tangent, p plus the reference angle. So Th2 equals p plus 125, which is approximately 4.39 radians. So the two solutions are approximately 1.225 and 4.39 radians. We have now learned a reliable method for finding all solutions to basic trigonometric equations within a given domain. We have now reached the 10-minute mark. If you're finding this video helpful and are looking for expert guidance in IB, A-Level, or IGCSE curricula, please contact DAR Tutors. We offer personalized online and home tuition to help you master these concepts and achieve your academic goals. You can find our contact information on our website. Now, let's continue with the rest of our lesson. Our final objective is to connect trigonometry with linear algebra by using the tangent function to find the gradient of a straight line. A fundamental relationship exists between the angle a line makes with the x-axis and its gradient. It states that if a straight line makes an angle θ with the positive x-axis, its gradient m is equal to tan θ. Let's prove this. First, consider a line with a positive gradient. Let's draw a right-angled triangle with the line as the hypotenuse. The rise is the change in y, and the run is the change in x. The gradient m is by definition rise over run. From the triangle, tan θ is also opposite over adjacent, which is rise over run. Therefore, m equals tan θ for positive gradients. Now, what if the gradient is negative? The angle θ will be an obtuse angle between 90 and 180 degrees. The gradient is negative rise over run. The acute angle inside the triangle is p minus θ. The tangent of this acute angle is also rise over run. So m equals negative tangent of p minus θ. Using our supplementary angle identity, tan PE equals tan θ. So we have negative of negative tan θ, which again gives us m equals tan θ. The identity holds for all gradients. Now let's apply this. Find the equation of a line with a y-intercept of 1 and an angle of p over 6 with the x-axis. First, we find the gradient. Isol ta ad p 6. We know from our exact values that tan plus 6 is 1 over root 3. So the gradient is 1 over root 3. The equation of a line is y equals mx plus c. We have m equals 1 over root 3 and c equals 1. Plugging these in, we get the equation y equals x over root 3 plus 1. Let's reverse the problem. Find the angle θ between 0 and p radians for the line y equals negative 1/2 x. From the equation of the line, we can see that the gradient m is negative 1/2. We know m equals tan θ, so tan θ equals negative 1/2. The tangent is negative, so the angle must be in quadrant 2. We use our calculator to find the inverse tangent of the absolute value, 1/2. Let's call this reference angle AA is approximately 0.464 radians. Our solution is in quadrant 2, so θ equals p minus a. This gives us approximately 2.68 radians. In this scene, we have successfully linked trigonometric functions to linear algebra, showing that the tangent of a line's angle with the x-axis is its gradient. We have now covered all the objectives for this chapter. We have now covered the main concepts of the unit circle and radian measure. Let's consolidate our understanding by working through some IB-style practice questions. Here's our first practice question. A sector of a circle has a radius of 6 centimeters and a central angle of 105 degrees. Find its arc length and its area, giving your answers to 3 significant figures. The first thing you should notice is that the angle is given in degrees. This means we must convert it to radians before using our formulas. So, take a moment to pause the video and try to solve this problem. Welcome back. Let's look at the solution. Step 1 is to convert the angle. We multiply the 105 degrees by p over 180, which gives us 7 pi over 12 radians. Step 2 is to find the arc length. L equals RT, so we multiply the radius 6 by 7t over 12, giving 7 pi over 2, or approximately 11.0 meters. Step 3 is to find the area. A equals 1/2 r squared θ. This is 1/2 times 6 squared times 7/8 over 12, which simplifies to 21 tt for 2, or approximately 33.0 square centimeters. Notice that I use the exact radian value in the calculation to maintain accuracy, only rounding at the very end. Here is our second practice question. Find the exact values of cos up 4, sin or 5 to 6, and tan 3 2 using the unit circle. This question requires you to recall the exact values for common angles, and to apply the concepts of reference angles and the ASTC rule for angles outside the first quadrant. Take a moment to work through each part. Let's review the solution together. For part A, P4 is 45 degrees. From our special triangles, we know cos of 4 is 1 over root 2. For part B, we have a negative angle. 5p6 is in quadrant 3. The reference angle is 5p6 minus p, which is pr6. We know sin p6 is 1/2. In quadrant 3, sin is negative, so sin 5p6 equals sin p6 equals 1/2. For part C, 3p2 is 270 degrees. This is a quadrantal angle. Looking at the unit circle, the point at this angle is 0, 1. Tan 3p2 is y over x, which is 1 over 0. Since division by 0 is undefined, tan 3p2 is undefined. Question 3 involves applying the Pythagorean identity. Find the exact values for sin th and cos th if tan th equals -3 and 3p2 is less than th, which is less than 2p. This problem is a two-part process. First, determine the signs of sine and cosine based on the quadrant. Second, use the Pythagorean identity to set up an equation in terms of a single trigonometric function. Pause the video and solve this now. Here is the solution. First, the domain 3p2 to 2p tells us the angle is in quadrant 4. In quadrant 4, cosine is positive and sine is negative. This is a crucial first step. Next, we use the identity sin th equals 3. Cosine th to substitute for sin th in the Pythagorean identity. Cos squared th equals th plus sin squared th equals 1. This gives us cos squared th plus 3 cos t squared equals 1, which simplifies to 10 cos squared th equals 1. Solving for cos t, we get plus or minus 1 over root 10. Since we are in Q4, we must take the positive value, so cos t equals 1 over root 10. Now we find sine using the relationship sin th equals 3 cos e. We get sin th equals 3 times 1 over root 10, which is -3 over root 10. Our answers, 1 over root 10 and -3 over root 10, align with the signs we predicted for Q4. This consistency check is very important. Our fourth question is a trigonometric equation. Find all angles th between 0 and 2p such that 2 sin th 1 equals 0. The first step here is to rearrange the equation to isolate the sine function. Once you have it in the form sin th equals k, you can use the method we learned to find the two angles in the given range. Pause the video and give it a try. Let's see the solution. Rearranging the equation, we find that sin th equals 1/2. Sin is positive, so our solutions will be in quadrants 1 and 2. The reference angle AKI, for which sin was p6 radians. This is our first solution, Th1. For the second solution in quadrant 2, we use the identity Th2 equals p so Th2 equals 2p6 equals 5p6. Our two solutions between 0 and 2p are p6 and 5p6. We can visualize this on the unit circle. A horizontal line at y intersects the circle at 2 points, one in Q1 at p6 and one in Q2 at 5p6. The graphical representation confirms our calculation. Our final practice question brings together trigonometry and geometry. Find the radius and area of a sector of a circle that has a perimeter of 36 centimeters and a central angle of 2p3 radians. The key here is to create an algebraic equation for the perimeter in terms of the radius. The perimeter is made up of 2 radii and 1 arc length. Remember, the arc length L equals rad. Once you find the radius, finding the area is straightforward. Pause the video and give it a try. Let's work through the solution. First, the perimeter of a sector is given by the formula P equals 2r plus L. We know P equals 36 and L equals RT. Substituting, we get 36 equals 2r plus reti, and we are given th equals 2p3. Substituting the given values, we get the equation 36 equals r times the quantity 2 plus 2p plus 3. To find r, we divide 36 by the quantity in the parentheses. This gives an exact value for the radius. 108 divided by the quantity 6 plus 2p. Approximating this, the radius is about 5.86 centimeters. Now that we have the radius, we can find the area using a equals 1/2 of r2 Plugging in our exact value for r, we calculate the area to be approximately 36.4 centimeters. This problem beautifully illustrates how algebraic reasoning and trigonometric concepts are integrated in IB mathematics. That brings us to the end of our exploration of the unit circle and radian measure. We've covered a wide range of essential topics. We started by defining radian measure and converting between radians and degrees. Then we used radians to find the arc length and area of sectors. We generalized trigonometry with the unit circle, defining sine as x, cosine as y, and tangent as y over x, and introduced the powerful Pythagorean identity. We also learned the ASTC rule for signs in each quadrant, derived and memorized the exact values for common angles, and explored important identities. We then applied these to solve trigonometric equations and to find the gradient of a straight line. Mastering these concepts is crucial for the rest of your IB mathematics journey. They form the foundation for calculus, differential equations, and many real-world applications. Continue to practice the techniques we've discussed to build fluency and confidence. If you need more help or want to deepen your understanding of these or any other math topics, remember to contact our tutors for personalized expert tuition. Thank you for watching.